Welcome back, everybody. This is chapter 10 again, and this is the second half of it for the part of secondary factors. I do not know why I'm having trouble with that. So this has actually got a lot of information in this section. I'm going to try and keep it manageable as far as time, but I need you to understand I will also do a separate one for just the formulas, okay? So right now I just want to go through the main things. When we talk about secondary factors, there are many of them that affect radiation and how much of that radiation reaches the image receptor and image quality. It's important for the radiographer to understand their effects individually and in combination. In this particular section, I'm going to cover focal spot size, source to image receptor distance, and it's SID, and you may even hear me say SID, and then object to image receptor distance, or OID, central ray, the grid, beam restriction, generator output, tube filtration, compensating filters, and patient factors. So let's jump right in. Focal spot size, you will see probably abbreviated by FSS for any future math problems. So if you see FSS, just know that that means focal spot size. Focal spot size is an important consideration for the radiographer because it affects sharpness. On the control panel, the radiographer can select whether to use a small or a large focal spot size. We kind of hit on that when we talked about the tube, so remember, there's only two choices. You either have a small or a large. The physical dimensions of the focal spot on the anode target in the tube is standard, usually range from 0.5 to 1.2 millimeters. So those can be anywhere in that range. But if you choose the small focal spot, they're usually a 0.5 or a 0.6 millimeter. And if you do a large focal spot size, it's usually 1 or 1.2. So even though it says it's that range, those are the ones that you will probably know. Now, you will never change the actual size of these. You just decide whether you choose a small one or a large one. Focal spot size is determined by the filament size, and when the radiographer selects a particular focal spot size, you're actually selecting a filament that's energized during the X-ray production. So you're either picking the small filament or the large filament. And in general, the smallest focal spot is the one that you should use for every exposure. Unfortunately, exposure is limited with a small focal spot size. So when you pick a small focal spot, the heat created during exposure is in a smaller concentrated area, and it can cause tube damage. So you would only want to pick the small when you're doing procedures that do not require a lot of heat. So with focal spot size is something called spatial resolution. Now I got this is a test image from a quality assurance program, and it just gives you an idea of what we're looking at here. But the definition of spatial resolution is the ability to distinguish two separate objects as separate. So if you are x-raying a hand and it has multiple bones, you need to be able to see each bone individually. And this is also known as sharpness, and the two terms are often used interchangeably. So I may say, you want a sharper image or you want better spatial resolution. So you want a higher resolution and you want more sharpness. So you could say higher sharpness, but for some reason those two don't go together. When you think about spatial resolution, they're actually measured in lines per millimeter, and that's what this is right here, lines per millimeter, and these are the actual lines. And what we're looking at is the space between these, and so the smaller the space between them, you still want to be able to see each of those lines individually. Now, do you need to know any of those numbers? No. Just understand spatial resolution or sharpness of an image is measured in line pairs per millimeter. And they are controlled mostly or pretty much completely by the focal spot size. However, the sharpness or resolution can be affected by all of these too. So the main controlling factor is picking the focal spot size, whether it's large or small, but the resolution can be affected by source to image distance, object to image distance, source to object distance, and motion. Here's an example. The size of the focal spot affects sharpness and spatial resolution recorded in an image. The bigger the focal spot size, the spatial resolution will decrease. The smaller the focal spot size increases spatial resolution. So how do you choose the focal spot size? Focal spot size influences the amount of unsharpness recorded in an image. So the larger the focal spot, the more unsharpness. So unsharpness is something you don't want. You want sharpness. If you need fine detail, then you're going to choose a small focal spot. And that is usually for like extremities. When you think about the bone, you want to be able to look at every bit of that bone, not just the overall structure. Now, you have not yet gotten into positioning, but in the next quarter you will, and it's important for you to understand when you take an extremity x-ray, you're looking at so much more than you think you are, and you'll get into that later. If you're radiographing a larger area, then you want a large focal spot size. And that's usually like for an abdomen, even a chest x-ray. So when you think of your body, look at your hand and then look at your abdomen. Even if you're a skinny person or a small person, your hand is so much smaller than the abdominal area. So if you are radiographing something larger, pick the larger focal spot. But a larger focal spot means there's more of a heat load, and it will give you more mass to choose from, but it will also require more from your generator and some of the other things that we'll look at. Now, with sharpness and spatial resolution, you need to know another word, and that's called penumbra. Penumbra is produced because of the angle of the anode and the divergence of the beam. It is an area of unsharpness that is on your image. The X-ray beam diverges from the source, and you know it kind of comes out in a TP type look or a triangle, and as it does, the photons continue to angle, so the outer part of the beam causes the penumbra or the unsharpness of the image. Penumbra is bad. That is the name for unsharpness. So if you increase your source to image distance, you decrease penumbra because more photons are perpendicular to the image receptor. So increasing it decreases penumbra. And then another factor that affects it is the focal spot size. The smaller the focal spot, the less the unsharpness, or the less the penumbra. So there is a formula that you'll need to know. Maybe you'll have to create work a problem with it, but more often than not, you just need to know the formula itself. So P is penumbra, FSS is focal spot size, OID is object to image receptor distance, and then SOD is source to object distance. So when you see these things and it says which of these would create more penumbra, you can go back to the previous slide where we talked about sharpness and resolution. And here's how this works. When you see this particular image, here is an object. So when you look at this, this is a larger focal spot size. So modern generators are equipped with safety circuits that prevents an exposure from being made if it exceeds the tube loading capacity. Therefore, it's going to take charge and help you in making the decision, but just look at these two images right here. So A is right here, a larger focal spot, and see what happens as it diverges. There's more out here. And then over here, B is a smaller focal spot size, and because of that, it varies at less. Now it's the same size object, but we've chosen a different focal spot. And then right here, this area of unsharpness, or the penumbra on the edges, is different. So one from the other. This is straight out of your book if you want to go back and look at that. Now, and they just call it spatial resolution. Here's another slide from another textbook, and this shows all three of those things that affect it. And let's look at all three of them individually. When you look at a larger focal spot versus a smaller, look right here at the difference in the penumbra. Much more on a large focal spot than in a smaller one. Here is with source to image receptor distance, or SID. So the closer you get to it, the more penumbra you get. Smaller, the further away that you get. And here's your object to image distance. Now, I always just say image instead of image receptor, but that I is image receptor. So if what you're x-raying here, and there's this much space between it and your image receptor, you're going to get more penumbra out on the edges. And so that way you want this to be closer to your image so that this is smaller. So just so you know, when the beam hits it like this, then it diverges even more. So those are the three things that affect, well, focal spot controls penumbra, the rest of it affects it. Now, there's one thing that I also want to throw in here. It's not necessarily in your text, but I believe it's very important. It's called motion blur. Any type of blur on your image decreases the sharpness of the image. This sharpness is also called detail resolution that we've already talked about. It's caused by your patient motion or your equipment motion. Now, sometimes the patient motion cannot be controlled and you shouldn't have any equipment motion, but it does happen. Since we're able to shorten our time with today's equipment, there's less motion interference, but it can still happen. So you need to be aware of your patient as well as the equipment whenever you go to take a radiograph. That motion blur will affect your sharpness of your image. And sometimes it's not seen as well on your screen when you've taken the image, but when the radiologist gets it on his computer, and that's another whole discussion, but their computers are usually better at seeing the image because they're the ones that are reading that image, and with that, they can see sometimes motion that you may not have caught. So just think about that and know that motion blur affects the sharpness of your image. So now let's move on to source to image receptor distance. Easy enough to say SID or SID. The distance between the source of the radiation, which is your tube, and the IR is called the source to image receptor distance. And it affects the amount of radiation that actually reaches the patient. Because of the divergence of the X-ray beam, the intensity of that radiation varies at different densities. So not only is it how far away from the patient it is, but then once it hits the patient, how much is actually left over. So the relationship between the distance of your tube and the beam intensity is described by something called the inverse square law. The inverse square law is extremely important, and it is one of those formulas that you need to know, but you also need to know how to work the problem. The inverse square law states the intensity of the X-ray beam is inversely proportional to the square of the distance from the source. Because the beam intensity varies as a function of the square of the distance, SID affects the quantity of radiation that reaches the IR. As SID is increased, so if you take your tube further away from the patient and the image receptor, then the intensity is spread out over a larger area, and that decreases the overall intensity of the beam that reaches the IR. If you decrease your SID, meaning you bring your tube closer to your patient and to your image receptor, the intensity is spread out over a smaller area, and that increase of intensity is shown up on your IR. Okay, so further away, intensity decreases. Get closer, it increases. This is a nice example. Now these are two different things right here, but it's showing you the same concept. Beam intensity varies as a function of the square of the distance, and this is a decrease. This decreases the overall intensity. So if at 20 inches, so if your tube is close, look how much of that beam is hitting what you're x-raying. But at 40 inches, so all you've done is move this further away, only this amount of X-ray is hitting it. So all this is lost. So the intensity is less at a further distance. And then this shows you the size of it. So as SID is increased, the intensity is spread over a larger area. So this is showing you how intense it is close up. Here, all that intensity is put into this size of a field, whereas further away, it's all spread out over here. But notice the shading of the blue. It's not as intense on this one. So just remember those. SID versus mass. Because increasing the SID decreases the X-ray beam intensity, you have to change your mass. And if you increase your SID, you have to increase your mass according to the proper amount with a formula that we're going to learn. When you decrease your SID, the intensity increases, therefore your mass must be decreased. And this is all about maintaining density. Maintaining consistent radiation exposure to the IR when you alter your source to image distance requires the mass be adjusted to compensate. And that formula is a mathematical calculation for adjusting when you change it. So here is the formula that is out of your book, and it's on page 126 if you care, but it's mass 1 or original mass over mass 2, the new mass, and that's your SID 1 over SID 2, but these are squared. So it's very important to remember the square on there. I can tell you on an exam, you may actually see these formulas and one will have squares and some of them don't. And I've seen where they'll put the square over here on the mass and not on this. So make sure it's your distance squared. Now this is a problem that they've already done. Proper exposure at 40 inches uses 25 mass. So there's our first math. And there's your 40 inches. The SID must be increased to 56 inches. What adjustment in mass is necessary? So you have 4 variables. You've been given 3 of them, and you've got to find for the last one. So 25 over x is equal to 40 squared over 56 squared, which is 1600 over, well, yeah, and 78,400. So square those out, then do your multiplications, and then divide, and your answer is 49. So when you go from 40 inches to 56, you're almost doubling your mass. And I don't want you to remember that. I want you to remember the formula, but also know that you just have to increase your mass to maintain density. Your standard distances used in radiography are there to provide consistency in radiographic quality. Most diagnostic radiography is performed at either 40, 48, or 72 inches. Now, some equipment, some has both, but some may actually say this, so you need to know these numbers also. 40 inches is equal to 100 centimeters. 48 is 122, 72 is 180. Now the 48 is not used as often as the 40 and 72, but know what those equivalents are in your other SI units. Standard distances are used in radiography to accommodate equipment limitations. Except for chests and cervical spines, a 40-inch or 48-inch is standard. The greater 72-inch is used for chest imaging because it decreases the magnification of the heart and it records the heart size more accurately. You will learn about that more when you get to positioning, but it is just a common thing to always do a chest at 72 inches if possible. Using the normal 40 to 48 inches for radiographs is the norm, but for chest x-rays and cervical spines, because what we are x-raying lies flat on the image receptor. But in the cervical spine, the spine is oblique and lateral images are further away from the image receptor, and we have to compensate. So let's go with some examples. If you take a knee x-ray and the patient cannot place their knee directly on the receptor, just pretend it's bent, they can't straighten it out, then you need to increase the tube distance to compensate, because now you have a larger object to image receptor distance. So you need your source to image distance to be more to accommodate for that. With a chest x-ray, and you haven't done one yet, and I understand that, but when you do a chest x-ray, you usually do them PA, which means the chest is up against the chest rack, and your heart is at least 6 inches from the image receptor. If you've actually taken a look at your upright Bucky, the Bucky itself is holding a whole lot of information, but your image receptor is back in there a little bit. So from where the heart is at the back of your body to the image receptor could be as much as 6 inches. Could be more if that's a bigger person. And 10 inches on an AP. So if you took your chest with your back up against there, then it's even further away. To compensate for that, we increased the tube distance to 72 inches. Now, we have now altered the intensity of radiation, but it has corrected the image distortion that would have been caused if you did it at 40 inches. So all of these things in the end actually work better to give us better spatial resolution. And I know that I'm going over more information that you may not think is necessary right now, but I do want you to know when you go to lab next week, you're going to work with these things, okay? So stand at the chest rack and see what it just looks like if you're PA versus AP. And by the way, those are terms you should already know from medical terminology and intro to patient care. Anterior posterior or posterior anterior. So here's an example. As the distance between the source and the IR increases, the diverging X-rays become more perpendicular to the object being radiographed, and it influences the amount of size distortion produced on your radiograph. A long SID creates less magnification than short SID. So here's A, it's very close to the body, and by the way, we're x-raying at kidney here. Now, because you're so close, that magnification is, there it is. Look how much larger it looks on here. But if we took our tube and moved it away, that same size image looks closer to normal here. So a longer SID creates less magnification. Now, this was all about talking about the standard distances, but you need to understand there are certain circumstances, such as trauma or mobile radiography, that do not allow for standard distances to be used. In these circumstances, you need to be able to determine the change needed in mass to obtain a quality radiograph. And that's what this is all about. So the 72 inches is your norm for a chest x-ray, and so if you adjust the SID to 56 inches, then you use approximately half the mass. These are just two circumstances right here. Then if you have a 40 inch and you have to change it to 56, then you would use twice the mass. Those are some norms, but you will probably not ever get a question like that. It's going to be odd numbers where you actually have to figure it out. Now, I don't have the formulas themselves in this presentation, but I will do one separately because you need to understand the inverse square law and how to adjust. But this is an example, so if you're in a trauma situation, you don't have time to sit and go, well, what do I need to change to get the correct intensity? You know, okay, well, I've moved closer, so I got a half the mass. I've moved further away, let's try twice the mass. Distortion. Distortion is a change in image size or shape. So when we talk about image size, then that's our magnification. When we talk about shape, that is controlled by tube angulation. And the two types of distortion are elongation and foreshortening. The size itself is controlled by OID and SID, but your shape is controlled by how much the tube is angled. This is an image, so you're trying to take a femur right here, and yeah, it's not by itself, it's within a body part. So if a femur is here, and it's the same on both of these examples, but on this one we've angled our tube this way. And so if that's caudal, which it should be because that's the top of the femur, no, I'm sorry, this is cephalad, so we're going up because there's the top of the femur, there's the head over here, then we've elongated that body part. But if we angle this way and the way it's coming, we're now angling caudally, now we have shortened it or foreshortened. So just know in one direction it elongates it and the other it foreshortens it. How do we correct that? That is strictly by tube angulation. If you were doing it with the tube straight up and down at a 90 degrees, you wouldn't have that problem. When distance is created between the object radiographed and the IR, we call this object to image receptor distance, or OID. Then when you do that, there's decreased beam intensity, because as the exit radiation continues to diverge, less overall intensity of the beam actually reaches the IR. So if you've got more space in there, then it's going to affect how much reaches the IR. When there is sufficient distance between the object and the IR, an air gap is created, and that air gap prevents the scatter from hitting the IR. Whenever the amount of scatter reaching the IR is reduced, then you have increased the contrast. The amount of OID required to increase that contrast depends in part on the percentage of scatter that exits the patient. For anatomic areas that produce a high percentage of scatter, then there's less OID needed. So it depends on how far away the object is from your IR and the anatomic part. So here's an example. So this is a cross-section of a person. So we're looking at their abdomen. There's the sternum, lumbar spine, the two kidneys again. So in addition to affecting the intensity of radiation that reaches the IR, OID affects the amount of distortion and spatial resolution. Just like we've said before, optimal spatial resolution is achieved if the OID is 0. If you have that body part directly on the IR, then you're not going to have image distortion. However, that's not realistic because there's always some distance created between the area of interest and the IR. As the exit beam leaves the patient, it will continue to diverge. So here it is leaving the tube and it's diverging. So this down here that continues through the patient is also diverging. OID is the only factor that affects the intensity of the radiation that reaches the IR, and the image contrast, and magnification, and spatial resolution. So this one measurement right here, which I find interesting because how's this person floating up above the image receptor? But if you think about realistically how this space happens, then it can actually affect all these things. Although the amount of OID necessary to adversely affect image quality has not been standardized, you should minimize OID as much as possible so that you can get the best image that you can. So sometimes it's out of your control, but when that happens, if this OID is more than you can do anything about, then increase this SID, because then by increasing that, then there's less that comes out at the end result. When distance is created between the area of interest and the IR, the diverging beam records the anatomic part with increased size distortion. So this is at a 90-degree angle and the object is at 90 degrees. But see how far here? It looks like it's a big femur bone. Down here it looks closer to normal because there's less object to image receptor distance. So you want that part as close to the IR as possible. So when I talk about size distortion, it's called a magnification factor. A magnification factor of 1 indicates no magnification. So you can think about that as 100%, which means that the size of the image matches the true object size. True object size on a radiograph is actually impossible because there's going to be some magnification. But if you've gotten your part as close to it as you can, then it's going to be as close to 1. Anything greater than 1 is a percentage of magnification. For example, if you have a magnification of 1.2, that means the image size is 20% larger than the object size. So if you know anything about fractions and decimals and percentages, 1.2, 0.2 is 0.20, which is 20%. So 1.2, 1 is the actual size, and then 20% larger. Anatomy that's posterior to the anterior chest wall is further away from the IR and magnified even more. And it may be helpful to know the measurement of the true object size in comparison. Once the magnification factor is known, then the subject size can be determined. Will you actually be asked to tell you the magnification of a specific object? It's possible. So we need to know these formulas. But what you need to know even more importantly is that if you change the SID and the OID, it affects the image size. Image size is mostly affected by this, but you can decrease it if you do this. So if we go to calculate a magnification factor, then you have to consider, again, we're going to first talk about the magnification factor and then put it with the SID and OID. The magnification factor indicates how much size distortion or magnification is demonstrated. It is expressed mathematically using the formula right here. And that is magnification factor is equal to the source to image distance divided by source to object distance. Now, we don't necessarily have this, but you should be able to have at least your SID or your object to image distance. So from the tube to the image receptor, and then from the object to the image receptor, and you subtract them, you get your SOD. And I love to say the magnification factor is SID divided by SOD, SID or SOD. Then the object size is the image size divided by the magnification factor. So all of these things put together can actually give you more information. Now I have a couple of problems here, but I'll go into it more in depth on another presentation so that you can get ready for lab next. Well, I'm going to say next week. I don't know when you're listening to this, but for week 6 you will need to know these things. So here's another way to look at it. Here is your source to object distance, so that's your SOD. Here's your source to image receptor distance, SID, but if you need your OID, then that would be the difference between here and there. Same thing, if you have 3 of your variables, you can always find the other in one way. So the size distortion or magnification can be increased by decreasing the SID or increasing the OID. And so that's the mathematical way of determining the magnification factor. And then you calculate the change in size. So anytime you have magnification, then you decrease your spatial resolution. So here's an example. You have an object that measures 2 inches when you are at 38-inch SOD and a 40-inch SID. What is the magnification factor? Well, there's your formula again. Magnification factor is SID over SOD, SID over SOD. So your SID is 40, your SOD is 38 here, so your magnification factor is 1.05. Calculate the size of the projected image now. So you have a 2-inch object magnified 1.05. 2 times 1.05 now your object is, you can determine your image is 2.1 inches, whereas your actual object was only 2 inches. That's not a huge increase. There are other variations that come along with this that you may find something that's magnified even more. Or you can use this formula if you don't have all of that information. So if you have an object that's 2 inches, the SOD is 38 and the SID is 40, yes, it's exactly like the other one, what will be the size of the projected image? So the first one, I'm going to show you here again, you want the magnification factor, SID over SOD. So you find this and you still have to multiply and get your image size. So let's go with this one. Object size over image size is equal to SOD over SID. So 2 over X is equal to 38 over 40. Now you're going to cross multiply. So 38X is equal to 80. I also want you to understand when you do this inch or this inch and this, it doesn't matter. If you multiply two things of inches, now you've got inches squared. So right here. This is not squared yet because you still have an x in the equation. But 38x inches is equal to 80 inches squared. Now you do your division. So to get x by itself on its side of the formula, you go 80 divided by 38. Because inches squared divided by inches, now your squared goes away. I know that sounds confusing, but that's just a mathematical thing. But now you have the answer of 2.1 inches. So you've got the same answer as when you did this other formula, but you were working in a different way. This is, sometimes you may be asked what is the magnification factor, but sometimes it may be what is your image size versus your object size. Okay? I'll try and explain it a little bit later. Now let's go on to central ray alignment. Shape distortion of the anatomic area of interest can occur from an inaccurate central ray alignment, so that's CR. And that's when you move the tube. Now we've already talked about the elongation and the foreshortening, but this is a different way to look at it radiographically. You can also have anatomic part alignment, which this is the new one, because we only talked about the tube before. If your tube is angled, then you get foreshortening and elongation. But if you change your anatomic part or your image receptor and they've been moved, that can also be a problem. So look at this image right here, and this is out of your book. So this is shape distortion when they're misaligned. First, look at this one. I know that you've not gone to positioning yet, but this is an elbow. And what's important here is that when you look at this elbow, this is proper alignment among the elbow itself, the tube, and the IR. Everything is the way it's supposed to be. And how do I know that? It is a quality image with minimal distortion. I know that because now we have the radial head and the capitulum. I never can say that word right. Look at this nice little space right here. Now this is the olecranon fossa, and I could go and name all these other bones, but it doesn't matter. This is the perfect example for you to see. That is what an AP elbow image should look like. The person has their arm correct, the tube is correct, and the IR is correct. Now, if you look at figure B right here, we've moved the IR and we've made an angle there. That's not good. So there is improper alignment among the tube, the part, and the image receptor. So either this is wrong or the person is wrong. And now compare this radiograph with this radiograph. Tube is still straight, but we no longer have this nice space right here at the radial head. Now they've kind of smushed on each other. And you see now how you can see the radial head coming through that bone right there. Well, if the radiologist did not know that there was this angle going on, he'd say there was something wrong with this person because this does not look the same as this. This is how it should look. Now the olecranon, I call that a hook, looks like it's hooked in a different way, and this bone is kind of jammed up into the humerus. And so he would say there was something wrong with this person. Now, if you have the image receptor correct and the person correct, but you angled your tube, now look at it. This is improper alignment, and now it has distortion because of the tube, and now look at the elongation of the olecranon. So not only is this wrong here at the radial head and the capitulum, but this looks funky. And because you're not used to seeing x-rays yet, you may not see that much difference in these, but trust me, that's the way you want an elbow AP image to look. So back to central ray alignment. It can be either from the image receptor being angled, the body part being angled, or the tube being angled. But it's the tube that can cause elongation or foreshortening. Okay, so keep that in mind. Let's move on to grids, just so y'all are not completely worn out before this is over. A grid is a device that's placed between the anatomic area of interest and the image receptor to absorb scatter exiting the patient. Limiting that amount of scatter improves the quality of the image. Much of the scatter radiation exiting the patient will not reach the IR if it's absorbed by a grid. The effect of less scatter or unwanted exposure increases radiographic contrast, which is a good thing. But you also need to know, and this is just a standard, grids are typically used only when the anatomic part is at least 10 centimeters. Now you can remember 4 inches, but I can tell you from experience, 10 centimeters is going to be your answer on a question if you see it. So if you have a body part that's only 6 centimeters, don't use a grid with it. And when you have a body part that's 10 centimeters or greater, then you also need to know you have to use at least 60 kV. And you cannot use a grid if you don't have at least 60 kV in your technique. So we have another whole chapter that we'll go over later about how a grid works, but for now you need to know what a grid is, how it improves quality, and how it actually works. The efficiency of a grid means that the more efficient it is, the more scatter it absorbs. That makes it more efficient. And that efficiency affects your radiographic contrast. Grids absorb some of the transmitted radiation that exits the patient and then reduces the amount of radiation that reaches your IR. So here's your beam, here's what's in the patient, and this is scatter that's coming out. But look, all this that hits there, some of that the grid actually absorbs. So only the useful information goes to the image receptor. So it's a good thing. You know, grids are used in a way that we need them. However, if you ever had to change your grids because they have different ratios, then we actually adjust the mass. So the higher ratio, and we're not going to get into that because that's in another whole chapter, it has a specific conversion. These are your typical ones, so you need to know no grid 5, 6, 8, 12, and 16. And they go in order of conversion 1, 2, 3, 4, 5, 6. So I'm just pointing out there is no 10 to 1, there is no 20 to 1, there is no 3 to 1. It's 0, 5, 6, 8, 12, 16. Now I don't know why, but that's just the way they are. So the grid conversion formula is a mathematical formula for adjusting the mass. And when we add a grid, the radiographer must use the correct grid conversion factor to multiply so that we know how to adjust our mass. Now the construction and the efficiency we'll go over later in chapter 11. But for right now, just know that we want the most efficiency possible. Okay. Grids are used to improve contrast. A grid can absorb secondary radiation that otherwise fogs the image. A grid absorbs up to 90% of secondary radiation depending on the ratio and the frequency of the grid. We'll talk about that later. But the usual method is to adjust the mass to account for the grid change, because mass is dependent on the grid ratio. And to determine the new mass, the correction factor of the new grid is divided by the correction factor of the old grid, and then that quotient is multiplied by the original mass. So here would be your formula. New mass is equal to the old mass times this correction factor. This shows it a little better. New, or number 2, mass, number 1, times grid factor, grid factor. So it's new grid over old grid. Here is a better way to look at that because we have a little problem. But again, remember that. The technique chart for a particular exam recommends using 90 mass and a 12-to-1 grid. What if you only have a 16-to-1 grid available? What new mass needs to be used? Although you'll probably never have to change a grid because whatever your department has, that's the grid you're stuck with. But we like to throw these just in case examples because back in the day you may have had two to choose from. So in this example, you're going from a 12-to-1 to a 6-to-1. Even though you haven't really gone over grids and what ratio is and what efficiency is, I think you can agree with me, just looking at those conversion factors, that a 12-to-1 grid means it sucks up more radiation. Therefore, it has more lead. So, more lead, less lead. So looking at the conversion chart, here's our formula. New mass is the old mass times new grid over old grid. Mass is your old mass, 90. These are the conversion factors that you got from that table. So it's 3 over 5. Now that right there should tell you we're going from more lead to less lead, so this number should be smaller because in the end we're going to come up with less mass. Got it? So you multiply that, 90 times 3 divided by 5, and then times 90, and your answer is 54. So multiply all that by the original mass, you have your answer. Bottom line, decrease your grid ratio, you decrease your mass. Now, there are no set numbers for that except for the conversion factor, so you will have to do this type of formula, but it's not hard, I promise. So looking at a decreasing grid ratio and working that problem, decreasing the grid ratio causes an increase in density because now more beam gets to the image receptor. It should also be noted that this increase in density is because more scatter reaches the IR, and that causes a decrease in contrast or a longer scale of contrast. But the good news is we have given less exposure to the patient. So if you go back and look at it, we started with 90 mass and now we are only using 54 mass. So your image may have a little less quality, but your patient was less exposed, and in the long run that may be important. So here's another problem. If you have 50 mass for a grid of 6-to-1, what new mass is needed for a 16-to-1 grid with the same density? So you're changing from a 6-to-1 to a 16-1. So we're going with less lead to more lead. There's our formula right there. If you look at your chart, then your new mass is 50 because that's what we were given. And now it's new over old, so 6 over 3. So you could automatically say, oh, well, 6 divided by 3 is 2. 2 times 50 is 100 mass. So multiply that by the original, you have your answer. So if you increase your grid ratio, you have to increase your mass. That's a lot of increase. We went from a 6-to-1 to a 16-to-1. We just doubled our mass. So increasing our grid ratio causes increasing it creates a decrease in density, and because of that loss of density, there's less scattered that reaches the IR, which increases our contrast or a shorter scale of contrast. And although you have increased the quality of the image, you've actually also exposed your patient to more. All of those factors must be considered when changing grid. So whatever it takes for you to remember, and we already know how mass and KV affect your image. Well, now if you throw in the thought of a grid, then you have to change your mass to adjust for it. And this box is in your book, so I just made me a picture on my phone and sent it to myself. Don't you love that? And then decisions regarding the use of a grid and grid ratio should be made by balancing the image quality and patient protection. To keep your patient exposure as low as reasonably achievable, grids should be used only when appropriate, and that grid ratio should be the lowest that provides sufficient contrast. So we throw this in here because even using grids and changing those factors has to do with the bottom line of radiation protection, and that's what we're here for. Get a quality image without exposing your patient to more than they need. All right, let's move on to beam restriction, the next item on our list. Any change in the size of your X-ray field alters the amount of tissue that we radiate. The effect is greater when collimation is greater, when imaging large anatomic areas. We perform exams without a grid, and if we use a high KV. But the first thing we want to look at is the beam restriction itself. So a larger field size means that we decrease collimation. And I want to spend just a minute on this because a lot of people will say, well, if I decrease collimation, then I have made my box smaller. Well, yes, you have. But it's not. It's decrease collimation. Collimation is the box, so if you decrease it, you've opened it wide up. A smaller field size means that we have increased the collimation. So let's look at these individually now that I've totally confused you. Hopefully every one of you have touched this in your lab, and if not, you will in week 6. A larger field size. This is what we're talking about right here. These are the controls. Now this may not look like the one in your lab, but these are the controls that you open and close to make the light coming out of here bigger or smaller. That collimation is where the X-ray exits. And so the larger the light, the more X-ray they're getting. So larger field size increases the amount of tissue irradiated. That means we've opened it up. We have increased collimation. A larger field size increases the amount of tissue that's radiated, but it also causes more scatter and it increases the amount of radiation reaching the IR. The increased amount of scatter reaching the IR results in less radiographic contrast. So, a larger field size means we have decreased our collimation. Decreased, because collimate means to make it smaller. So a large field size, as we opened it up, we have decreased our collimation. And yes, that gets very confusing. Now, here's that same tube. A smaller field size, we've made our box smaller, less light coming out. We have increased collimation. But by making the box smaller, we've let less X-ray through and less tissue is radiated. That reduces the amount of scatter and the amount of radiation reaching the IR, and that decreased amount of scatter results in higher contrast. But it requires an increase in mass. So just because it's either a wide open field or a smaller field, and you should collimate every single time when you do an X-ray, don't leave it wide open, then that does affect how your image looks and the radiation to your patient. This box again is in your book. When you perform a radiograph, the radiographer should be aware of the anatomic area of interest and limit the field size to just beyond that area. Collimating to the appropriate field size is a basic method for protecting the patient from unnecessary exposure. This is a perfect example of ALARA, just using your collimator correctly. Now let's move over to the generator. So, exposure techniques and the amount of radiation output actually depend on the type of the generator that's used. Now, can we choose the generator? No, it's whatever your unit already has. But today's generators with more efficient output are usually 3-phase or higher. We call them a higher frequency unit. They're more efficient, they require lower exposure settings to produce an image when you compare it to a single phase. So the radiographer must be aware of the generator output when using different equipment and when performing examinations in different departments. Now you may go to a facility that has 3 different imaging equipment and they may all have a different generator. They usually don't, but they could. But let me see if I can give you an example without you seeing it. If you took an image of someone's knee and you have a single phase generator, you're going to need more mass than if that generator was a 3-phase. So it requires more exposure, that means more mass. So, in addition, generators must be calibrated periodically to ensure they're producing consistent radiation output. And we'll talk about generators in general later, and then those different tests that come along with that. Okay? Now we're up to tube filtration. We discussed tube filtration earlier when we were talking about the tube itself, but increasing the amount of tube filtration increases the percentage of higher penetrating X-rays to lower penetrating X-rays. The amount of tube filtration should not vary. Small variations in the amount of it should not have any effect on radiographic quality. According to, and you need to know what that is, the NCRP is the National Council on Radiation Protection and Measurement, but it's not in the acronym. I've always thought that was interesting. Tubes that operate over 70 kV are required to have a minimum of 2.5 millimeters of aluminum filtration. Now, that's when they're operated at 70 kV or higher. The variability of an X-ray tube's filtration should be checked as part of routine quality controls. X-ray tubes that have excessive or insufficient filtration may begin to affect image quality. So, know this right here, NCRP requires a minimum of 2.5 millimeters of aluminum on units operating at 70 kV or higher. Now, here's something that's even more important. We can increase filtration. Now, I'm not going over decreasing it because you can't. What does this say? You have to have a minimum of 2.5 millimeters. You cannot go less than that. But you can increase. And as a result of increased tube filtration, your beam has increased energy, more kV, and it increases the amount of scatter that reaches the IR. That increased energy and scatter production, so that increased X-ray energy, or the kVp and scatter, can actually decrease our contrast. The amount of tube filtration should not vary greatly, therefore small changes do not have a visible effect on the radiographic contrast. But you need to know that filtration in general does have a role in how well your image looks, which is part of spatial resolution. And as I said before I started this slide, remember, you don't have a choice to decrease, you can only increase. So increased filtration can come in the form of a compensating filter. We also discussed it before. Now remember, a compensating filter is not the same as a tube filter or an H or half value layer. When imaging an atomic area that varies greatly in thickness, such as a foot, a compensating filter can be placed in the primary beam to produce a more uniform exposure. It evens out the part and makes the image look better. Now, I'm going to tell you, in the real world, people don't do it anymore, but I do remember taking all my foot x-rays with this compensating filter just so that it was a better image. The problem is that was back on film, where, remember when I say once you've taken it, it's done, there's nothing you can do to adjust it. In today's world, a lot of places just go ahead and take it as normal, and then they expect the radiologist to adjust on their screen. Not saying that it's correct or not correct, but you won't probably see it much in the field, but know what it is just in case. That's where you put it in the primary beam. So the use of compensating filters requires you to increase your mass, which is another reason we don't use it as much anymore. So the amount of the increase depends on the thickness and the type of the filter. And additionally, when you use one of these compensating filters, it increases the exposure to your patient. One of the other things that comes along with that is when you do a scoliosis film, because you want the entire spine in one view, then a lot of people may still use it here because that way it evens it out through the chest and then in the abdomen where there's so many variations. All right, now my favorite part is patient factors. So differences in our patients require adjustments in our technical factors. Now, we'd have another whole section where we'll talk more in depth about it, but I want to go over these today because every single one of these factors can make a difference in how you adjust your techniques. These are additional secondary factors, so they still fit in here, but I want you to get an idea of how it works. So the things we're going to talk about are body habitus, part thickness, pediatric patients, geriatric patients, pathology, and then some special circumstances. When it comes to the body habitus, that is the general form or build of the body, including the size. And it's important for you, the radiographer, to consider body habitus when you select your exposure techniques. Now, it's real easy for me to tell you this because I say you need to change. Well, in reality, on your controls at your lab and when you go to clinical, you actually select big person, little person, average person. But you need to understand why you make those changes. And I just want to go over them a little bit more. Here is the 4 different types, and I hope you see these well. Here's the sthenic. That is the average. The hyposthenic is similar. I'm going to go through each one of these separately. And then a hyper and an asthenic. But I like this image that's in your book because this gives you an idea of what their chest x-rays and how they vary. So this is an average build person. This is a chest x-ray. Now, you haven't even done any positioning yet, but here's the apex, here's the diaphragm right here. This one looks very similar, except it's not spread out as much. It's actually sucked in a little bit. And then this is a larger person. See how the lungs appear shorter? Well, it's because there's more stuff down here that's pushing those diaphragms up. So that's giving you an idea right here. And then this is a long, skinny person, and that's how their chest x-ray looks. Here's an image of them from the outside. So when you see these people, this is the average, and this is close to average. Those are the main body types, but then you have your very slender, and then I love the word massive, but that's going to be your really large person. The sad thing is, in today's society, and myself included, I mean, there's more overweight people than there used to be. So we're starting to get closer to more of these than what's actually documented. So the first one is sthenic, which is approximately 50% of the adult population. And this is called the normal or the average build. Okay, this image right here, just so you know, means this is the chest, there's the heart, this is the diaphragm, intestines, pelvis, this is the gallbladder, and then there's the stomach. I'm going to put all 4 of them together at the end and I'll discuss the differences. Hyposthenic, you need to know that they are about 35% of the population, very similar to sthenic, but they're more slender and tall. And this is called also the normal or average. With the hyposthenic and sthenic, they account for about 85% of the population of adults. Then you have hypersthenic, a large stocky build accounting for about 5% of adults. I honestly think that number has probably changed, but this is still the number that's in our textbooks. You probably had all this in your patient care class also. These individuals have thicker part sizes compared to sthenic or hyposthenic, so exposure factors are much higher. So it is something you do need to understand. And then you have the asthenic, which is only 10% of adult populations. These are very slender body habitus, accounts for smaller sizes, and these exposure factors are going to be more of the lower end of the chart. The hypersthenic and the asthenic body habitus types are more extreme and less common. So back to what I said originally, your sthenic and hyposthenic are the most common. So when we look at these four together, the first thing I want you to notice is this is in general, not applying to every single person, but it's pretty darn close. Here are the lungs of a large person. When someone has more abdominal fat, their body spread out a little bit, and that gives the ability for things to push the diaphragm up, causing the lungs to be smaller. And in general, they usually have a larger heart. And notice how their heart is taken up. It didn't change that much, but now because the lungs are not as filled in, this has taken up more of their chest area. And because of that, look at where their stomach is in relation to the sthenic person. This is how your stomach should be. It should hang down and then around and then go into your colon. But in a larger person, all this, see how this is more spread out and it's pushing? Then it also makes their gallbladder way up here too. This has nothing to do with radiology, but I also do ultrasound, and I can look at a person when they walk in the door. I know where to put my probe if I'm looking for a gallbladder. If they look like this, it's going to be hiding up here near the diaphragm. And then let's go to the other extreme. Look at this skinny person's gallbladder. It's down in the pelvis. I have actually found them in the pelvis before because they're just kind of start falling down. So when you compare this diaphragm to this diaphragm, and then they seem to go down a little bit more, creating more space for air to be in their lungs, and it changes the look of their heart. It changes the appearance of their stomach. Look how much longer these stomachs are here on these skinny people. It's almost like it just falls. And those are pretty accurate when it comes to it. So that's just their body habitus, knowing that the larger the person, the more technique in general that you have to use. Now, what have you also noticed? We're talking about the torsos of these people and their body habitus. But at the same time, this person's arm could be a lot bigger than this person's arm. So it is every body part, but it's mostly changes in the torso itself. The thickness of the anatomic part being imaged affects the amount of X-ray beam attenuation. So we've talked about attenuation before, but a thick part absorbs more radiation where a thin part transmits more radiation. So with a thicker part, to maintain exposure, you have to increase your mass. In addition, with a thinner part, then the mass must be decreased. Because X-rays are attenuated exponentially, a general guideline is that for every 4 to 5 centimeters of tissue, you adjust your mass factor by 2, well, by a factor of 2. This is the image in your book. So you're seeing 100 X-rays. So when you go through 5 centimeters right here, you've dropped down to 50, and that's the whole. You adjust your mass by a factor of 2. So if it goes 5 more, it's 25. I actually prefer this one right here. So this is done at 4 centimeter intervals, and it shows you we started out with 1,000. 4 centimeters, we only have 500, and then halves again, then it halves again, and it halves again. And if you go to 20 centimeters, you've only got half of that 63, which is 31.5. And so less reaches in there, so that therefore you have to have more starting with to reach your image receptor. So keep that in mind. So here's another example. The amount of radiographic contrast. So looking at our contrast is influenced by the anatomic part that we're radiographing. The anatomic or the atomic number and the thickness of the tissue and cell compactness affects its absorption characteristics. And then the absorption characteristics of the anatomic tissue creates the range of densities and brightnesses that we see on our radiograph. So now, this is 3, but they're all coming from the same tube, and this is a chest x-ray of someone laying on their back, or they could be standing up. So this gets transmitted. Well, this gets absorbed because it went through heart, which is different from the lung, and then it stops in the spine because the spine sucked it up. This one scattered, and so it kind of stayed, and then that's all we got down here. So knowing what it's going through actually makes a difference in our radiographic contrast. So that's why there are different techniques for a chest x-ray versus an abdomen x-ray versus a skull x-ray. This is another chart that is not in your book, but I think it's very important for you to know. When you talk about atomic numbers, lung, fat, and muscle are different, and then look at your bone, much different. And you can have contrast agents in that body also that you need to account for. So air is low, but iodine and barium, and then if there is lead. So, all of these different things you have to take into consideration. Anatomic structures that have a wide range of tissue composition demonstrate high subject contrast. So when you have an object that's more muscle, water, and fat, it's lower contrast than this. It's that bone and air differences where you see more contrast. So anatomic structures that are similar have low subject contrast. You cannot control the composition of the anatomic part, but changing the KVP alters its absorption and transmission. And knowing those absorption characteristics and how KVP works gives you the desired level of radiographic contrast. So when you think about that, you definitely need to know how to adjust. In week 5, we talked about primary factors. Now we're talking about secondary factors, so you need to know about them. Here's another one I think is really cool. So I don't know if you want to take notes from it, but if you increase the thickness of your patient, which you can, it just comes that way, you increases attenuation, increases absorption, but it decreases transmission. And you can look at all of these too and see how they actually relate to one another. As the thickness of any given type of anatomic tissue increases, so does the amount of scatter, and the contrast decreases. Using a higher KVP for a thicker part only adds to the increase in scatter. An increased scatter continues to degrade the quality of the image because it creates fog. And that fog, so here's a smaller person and a larger person. All of these little purple things right here are the scattering x-rays. And so less gets for a smaller person, and then this is more here. So all of those changes have to be considered when you're looking at your patient. Okay, now let's look at some of those extra ones that I've thrown in here. So pediatric patients. Pediatrics can be a technical challenge for radiographers for many reasons. They're smaller. They can require lower exposures, and that's with KV and mass. And sometimes with the pediatric chest x-ray, then you have to have a fast exposure time so you can stop the diaphragm. So you're going to need a faster time. A fast exposure may eliminate the possibility of using an AEC, which we haven't even discussed, but understand that that's something that you'll learn. And so picking the mass with the fastest time is very essential. And in exposure factors for bones, because there's possibility of having lower bone density in a child, let's take the skull for an example. An adult skull for pediatric 6 years of age and older because the bone density has already developed. However, the rest of the body of that pediatric patient probably has not developed as much calcium. So it's recommended that a radiographer decrease your KV by at least 15% to compensate for lack of bone density. That's where we will also choose the size differences on your control panel versus a large, small, and you may even have a lot of the newer equipment has pediatric sized techniques. So everything else on a child could be different. Let me show you this example right here. I bet you didn't actually realize, unless you've seen some of these x-rays before, this is a child's hand and this is an adult's hand. And I can tell you, I remember the very first time I saw a child's hand, I'm like, oh my gosh, they don't have all their bones. Well, guess what? They're not formed yet. They have not completed all of their development. So these little carpals are going to become this. These are our carpal bones down here. And then your metacarpals are here, and then they're going to come into this. So, you know, you don't even have, this is a sesamoid right here at the thumb. They don't even have that yet. So this right here, there's more tissue in here than there is bone. And look how you can see through this. That means there's less calcium in there. So all of those techniques, it just means you have to make a change when you have a pediatric. Don't be scared of them. They're not harder, but they do move a lot. So, you know, you've got to take all that into consideration. Then we have the geriatric patient. Now, this is not actually listed in your text, but I'm pointing it out because, again, you have to make adjustments. Every geriatric patient does not have this happen, but you need to be aware to know what changes to make. Sometimes, and especially in women, bone loss starts around the age of 50 and continues to decrease in density. And not only are we losing some calcium in the bones, but notice how you've changed in stature also. So this person is going to be a little more difficult because that curve right there is something she can't control. She may not be able to lay completely on her back. There could be a lot of different things. If a patient appears to have osteoporosis, something you'll talk about later, then you have to adjust your technique. And then, like I said, some geriatric patients will not be able to stand or lay down completely flat. You need to know how to adjust the technique if you use a different positioning. In your first class that you had here, the Introduction to Radiology and Patient Care, you probably talked about how you need to be careful of older people with their thin skin. Well, not only do we have to worry about possible skin tears in some people, you need to know that their skin is not as thick, so you don't have to have as much exposure to go through. So all of these things need to be taken into consideration. Here's another one that may or may not be in your text to this degree, but I think it's important that you know it. Technical factors may need to be altered because of pathology. Now this is when you know that pathology before you take an x-ray. You may not know it and you don't adjust it, and then when you see it come out you go, ooh, I'm going to have to change that. So there are two different types of processes. Additive disease processes, and that's an increase in fluid, bone, metal, or tissue density. How do people get metal? Well, what if they've had a hip replacement, a shoulder replacement? Anything that they've got in their body is going to create a reason to increase your mass by 30 to 100%. It just depends on what it is that they've got different. But that's an additive disease process. Then you have a subtractive disease process. This is less absorption of the beam because there's increased air or decreased tissue, just like the thin skin that I pointed out. With that, you're going to decrease your technique by as much as 15%. Now, how do you know how to change these? When you get to your control panel and you have your different patient sizes, that's one thing. That takes into account the patient itself. Then you have these little buttons called plus and minus. Those are the ones that you change for pathology. So if you have a chest x-ray and you already know that they have pneumonia or fluid buildup, you're going to use the plus so that you get a little bit more technique in there. And say they have osteoporosis, and you already know that, then you're going to push the minus button so it doesn't use as much technique. Because when it comes to pathology, we can't do this. Take a minute and read that. So your x-ray showed a broken rib, but we fixed it with Photoshop. We cannot Photoshop our x-rays when we take them. So, just a little humor to get through the rest of this. Here are some of the additive disease processes. Again, these are not part of your text. You're going to learn about them later, but these are some of the things that may add technique to your exposure. An aneurysm, ascites, cirrhosis, the skeleton. Here's some of these. Don't confuse osteopetrosis with osteoporosis. And then chest, atelectasis, all of this is increased fluid. And then you can have abscess, edema, or sclerosis. Here's some destructive, and there's that osteoporosis. So that's decreased bone. But you can also have a bowel obstruction or free air that is a destructive. And so just looking at some of those. And if you have any other questions, just look at some of these and remember some of your medical terminology that you should have already had. Here's some special considerations to think of too. Again, these are not necessarily in your text, but I want you to know about them. Hands and neck are your most common soft tissue. If you had to do a soft tissue of a hand to visualize something that's in there, wood, glass, or something you swallowed in the neck, then you reduce your technique. And then you have cast. Now, a fiberglass cast is radiolucent, so you don't have to change your technique, but a plaster cast you do. We don't see plaster cast as often, but they'll use them a lot of times for specific reasons. And you need to increase your techniques by 2, and it depends on if it's a fresh, wet plaster or a dry plaster. So that's important also. And then you have contrast media. Again, we're not up to contrast media, but knowing what they are, positive ones are things like barium and iodine, and so you have to increase your technique. And the negative ones are air or CO2, and they increase radiolucency, so you need to make sure that you decrease your technique just a little. All right, we have finished the overview of the secondary factors that I talked about, and I'm not going to read them off again, but you need to make sure that you know all of these and how they affect your exposure changes. We covered these objectives. We talked about recorded detail, distortion, grids, beam restriction, image receptor exposure, exposure factors that affect radiation exposure, and then some exposure technique modifications for patient factors. I went over a few more than those, but make sure that you know all of them. I will do another special live class, or I may just go ahead and record it so that you can have it, but to go over some of these calculations. But you need to know these formulas. You need to calculate the change in mass for changes in source to image receptor distance, which is the inverse square law, magnification factor, and the object percentage formulas, and then the grid conversion and how you change your mass when you add or remove a grid. So for radiation protection, we've also talked about whenever possible a higher kV and lower mass should be used to reduce patient exposure. Increasing kVp requires less mass to maintain the correct exposure and decreases the radiation dose to the patient. So if you change from a 70 to 81, a 15% increase in kV requires half the mass, and a higher kV increases beam penetration, therefore less quantity, and so on. When you have to worry about the beam restriction and the anatomic area that you are x-raying, limit your field size to just beyond that area. Collimating appropriately is the best way to protect a patient from unnecessary exposure. Decisions about using a grid and the grid ratio should be balanced between image quality and patient protection. They should only be used when appropriate, and it should be the lowest that provides sufficient contrast. And although the computer can adjust image brightness for technique exposure errors, routinely using more radiation than required is unnecessary. because it increases your patient exposure. And even though the digital system can adjust for it, it is unethical to knowingly overexpose a patient. So, with that being said, we have covered a whole lot of information, and keep looking over it. And I'm just going to point out here, now this is supposed to be an elderly lady, so here's her x-ray, there's her cane. You're not ever going to x-ray her cane or her shoes, but there's a replacement hip right here, and then she's pulling along a little baggie. I'd love to get you to look at that closer and figure out what all's in there, but that one's always kind of cool to me. You can kind of look at all those different things. Why has she got a bird in there? There's her glasses, her knitting needles, all these really kind of cool things. So, and then right here on her little legs, boy, those bones don't look good at all. We've covered a lot. Keep looking over it. Watch for my formula and calculations conversation to come, and be prepared next week for a midterm exam. So not only the whole amount of stuff you've already covered, but this week's information is going to be on there too. Thank you and goodbye.